Hello, welcome to Fundamentals of Acoustics. Today is the fourth day of the seventh week of this course on acoustics, and in last three lectures we have been discussing how sound waves interfere with each other, and specifically speaking, in last two lectures we have developed expressions for interference of waves, first in presence of two sound sources separated by a distance d, and actually in last class we discussed how sound sources interact when there are four sources. So, let us very quickly recap these results. So, the theme is interference from multiple sources. So, that is our theme, multiple sources. What happens when there are multiple sources? So, if there were two sources S1 and S2, and we were interested in pressure at r, theta and t location, and this angle was theta, then the result which we had developed was pressure at far field is equal to term A times sin 2 alpha divided by sin alpha. Of course, this result is correct as long as some important assumptions hold. What are those assumptions? That d is small or actually very small compared to r, where d by 2 is this distance and d by 2 is the distance from midplane to the second source. The second thing was that phase of S1 is same as phase of S2, and that is equal to 0 degrees. And the third assumption which we had made was that the volume velocity magnitudes were same. Okay. So, if these three assumptions hold, then this is the expression. Okay. So, that was for two sources. Then we developed an expression for four sources. So, this was for two sources, and then we developed an expression when there are four sources. So, in this case we are still, the point is still far away. Let us say this is the point P r theta t, and sound is coming from all the four sources, and these distance, separation distance between each of these sources is d over 2, and the sources are designated as S1, S2, S3, S4, and the assumptions which we had made earlier, similar assumptions are made in this case also. So, in such a case P of r theta t equals A sin 4 alpha divided by sin alpha, and alpha we had defined as, so alpha was defined as omega d sin of theta divided by 2c. Okay. And A was defined as, so it was a relatively largest expression. So, it is Vv divided by 4 pi r j omega rho naught and E to the power of j omega t minus r over c. So, that is what A was defined as. I can continue adding up sources, and what I will find is that I will find a very specific and clear trend that for 6 sources So, if I have 6 sources, my P r theta, it will be A sin 6 alpha divided by sin alpha, and so on and so forth. So, if there are n sources and n is a even number, I can generalize this trend through principle of mathematical induction. So, I can say it is equal to A sin n alpha divided by sin of alpha. Okay. Now, n could be an extremely large number, it could be infinite. An example of n sources could be that suppose you have a string, for instance of a guitar or something, and if all points in the string are moving in and out by the same amount, because volume velocity we are saying is same, and they are moving in phase to each other, then that kind of a source could be considered as an array with n sources. Okay. So, now what we want to develop is an expression for what happens when there are n sources, because mathematically if n is large or theoretically if n is infinite, then we cannot do this computation, because I cannot use infinity to do calculations. So, I have to make it mathematically in some different form. But if there are sources, number of sources is very large, then P r theta t equals A sin n alpha divided by sin alpha. Okay. Now, consider an array. So, there are lots and lots of sources, and each of these sources are separated by a small distance d, and as so suppose the overall length of the array is b, and b is a finite number, maybe the string is 20 centimeters long, so it is a finite number, and if n is extremely large, then d is equal to b over n minus 1, where n is the number of sources, and if n is extremely large, then this can also be approximated as b over n. So, d is b over n. So, I can write b equals n times d. So, complex pressure which depends on r theta and t is equal to A sin and n times alpha, and alpha is pi d sin theta divided by lambda divided by sin of alpha. So, where alpha is again pi d over lambda sin of theta. Okay. Now, once again in this expression I have to use the term n, which is extremely large, and I have to use this expression d, and d is also extremely small. So, in one case I am having an extremely large number, theoretically infinite, in the numerator and a theoretically 0 number in the denominator. So, I cannot do this mathematical operation. So, we have to somehow transform this equation into something usable. So, that is what our goal is. So, we have seen that n times d equals b. Okay. So, what we do is n times d is b, and b is a finite number. So, I can write it as A sin b pi over lambda sin of theta divided by sin pi d over lambda sin of theta. Okay. So, I have gotten rid of n and d in the numerator. Now, I want to do something similar for the denominator also. So, what we do is We know that pi d over lambda times sine theta is very small. Why is it very small? Because this finite string which is having n sources and n is an extremely large number, and if n is extremely large then d has to be very small. If d is small, pi is finite, lambda is finite, sine theta cannot exceed 1. So, pi d over sine theta is also extremely small. So, for that case, this relation can be expressed as a sine b pi over lambda sine theta divided by pi d over lambda sine theta, because sine of a small angle is same as the angle itself. And now what I do is I multiply the numerator by n and divide the numerator by n. So, I get a n sine b pi over lambda times sine theta divided by dn times pi sine theta over lambda. Now, dn equals b, because d is the distance between sources, this is the expression dn equals b. So, I can rewrite it as a n by b pi sine theta by lambda times sine of b pi over lambda times sine of theta. Okay. So, that is my expression for p r theta t. Now, what we do is, so suppose this is the array with all these infinite or extremely large number of sources, and this array is b units long. Let us say this is my 0 degrees. So, if point P is located here, then this is point P r theta t, okay, and this angle is theta. So, what this expression tells us is that at angle theta, what is going to be the complex pressure. Now, for the same value of r, if I have theta equals 0, if theta is equal to 0, if theta equals 0, what will happen? The sound pressure is going to be maximum at theta equals 0. Why will it be maximum? Because first thing is all the sources are moving in and out at the same time. So, at theta equals 0, the contribution from this source and a source which is just opposite of the median line will add up, which are equidistant, because the distance travelled by sound wave from this point to this. So let us say, so this is P1 or not P1, I will use a different term. So let us say this is point y1 and y2. If y1 and y2, and this is my, so at this location, what is P? P radius is r, theta is 0 and time is t. So, the contribution of y1 and y2 will add up and they will all come in phase. Similarly, y3 and y4, they will also add up. So, this, the sound pressure level at P r0t, it will be maximum. At other locations, they may constructively or destructively interfere. Okay. So, what that means is that this term, it represents the complex pressure at theta equals 0, right, that is what it means. So, if I take the magnitude of both the sides, then the magnitude of LHS is magnitude of the numerator times this entire factor. So, the magnitude of sounds at position theta is equal to magnitude of sound at angle 0, which is P 0, divided by B pi sin theta by lambda times sin of B pi by lambda sin of theta. Okay. So, this is our final expression, and what this expression tells us is that at any angle, if I have to calculate the value of sound pressure level, I can calculate it in terms of theta and lambda and B as long as I know the value of pressure at theta equals 0. So, the final comment, so if P 0 is known, so this P 0 is then P r theta t can be calculated. Here theta can be calculated, and here P 0 is not atmospheric pressure. This is just because we have run out of symbols. Rather, P 0 equals sound pressure at radius r and theta equals 0 degrees. Okay. So, that is there. So, this concludes our discussion for today, and tomorrow we will like to switch gears and we will introduce one term called directivity, and the day after that we will talk about power in context of spherically propagating waves. So, that is pretty much for it today, and I look forward to seeing you all tomorrow again. Thank you.